All right, now that we've talked a bit about units, we're ready to delve into experimental physics. When I was an undergrad at Virginia Tech studying physics, I used to listen to conversations between professors. There were experimentalists and there were theoretical physicists. We'll dabble in a little bit of both, but it was really funny to kind of hear them jab at each other. Little nerd fights. It was great. I loved it. So by the end of this video, you're going to learn the difference between accuracy and precision in experimental physics, what value you should round your numbers. Believe it or not, that actually matters. Every single scientific report you see, the numbers are rounded very, very carefully, especially if it's a published and peer-reviewed work. I'll talk about why we even care about Sigfigs and experimental uncertainty. So real quick, the difference between accuracy and precision. Accuracy is how close are your measurements to the actual value. So if you look at this target, you can see a few little attempts, and none of them are perfectly on the bullseye, but if you took an average of them, they pretty much would be. It would average out to a bullseye. So it's pretty accurate, but not necessarily precise. Now, precise means how close are your measurements to one another. So if let's say the proper value is 7, and I continuously measure 4, 4, 4.1, 4, 4. I got very precise data, don't have very accurate data. So ultimately, you want data that's both accurate and precise. And then there are significant figures, which you have to deal with when you're doing experimental physics. George Washington was a significant figure, but in science, it's something totally different. It's pretty much just telling how confident you are in your results. So if you have a whole mess of decimal points, no, that's wrong. If you have a whole mess of numbers after the decimal point, there we go, then you're very, very, very confident that you've measured it to this value. So what is a significant figure to begin with? Well, any non-zero digit is significant. So 1, 2, 3, 4, 5, 6, 7, 8, 9, all are significant. It gets a little bit sticky and tricky when you get to zeros. So if you are on the left of a decimal point, any zero between significant figures is considered significant. So for example, the number 1003. Well, my 1 is significant in that it is a 1. My 3 is significant in that it is a 3. My 2 zeros are now wedged in between these other two significant figures, so they therefore are both also significant figures. So this would have 4 sigfigs. Okay, not too bad. It gets a little bit weird when you start getting numbers that are where you have zeros at the end and you're still to the left of a decimal point, like 1300. The 1 is significant, the 3 is significant, but these 2 zeros, it's kind of hard to tell. So you would be able to make an argument for 4 sigfigs, for 3, or for 2 with this number. I don't really like it. So we'll talk about ways to get around this mess that I don't really like when we go beyond the decimal point to the right. So if it is final zeros, for example, 1.0200, the very final zero to the right of a decimal point, boom, automatically significant. The 1 and the 2, automatically significant. The 0 between the 1 and the 2 is significant, and check it out, the 0 between the 2 and the final 0 is also significant. Nice. Now it's insignificant only when it's immediately to the right of the decimal point and it's before any other sigfigs. So 0.0001 only actually has one significant figure. And all these opening zeros, nah. Now, the ambiguity I talked about earlier with that number 1300, where it could have been 1, 2, 3, it could have just been 2, 3, or 4 sigfigs here. Use scientific notation. I could also write this as 1.30 times 10 to the 1, 2, 3. Boom. Once I have it in scientific notation, now these zeros that were ambiguous are to the right of the decimal point, so they follow these new rules. So the way I just wrote it, this number would only have 3 significant figures, the 1, the 3, and the ending 0, because it's to the right of a decimal point now. I could have written it as 1.300 times 10 to the third, in which case it would have 4 sig figs. The number that I include really depends on my incoming measurements. So here are your sig fig rules, how to know how many numbers to include. Should I do 3? Should I do 4? There are different rules for adding and subtracting than there are for multiplication and division, just like with units. Can't add units unless they're identical, but you can multiply or divide any units. You also have different rules for sig figs. When you're adding or subtracting, look at what you have coming in. So let's say I'm adding 2 different distances to find a final total distance, for example. So those are your arguments before adding or subtracting. Count the number of decimal places, and then notice which number coming into your measurements has the least amount of decimal points, and round your final answer to that number of decimal points. Notice that I'm saying decimal places, not sig figs. When you're just adding or subtracting, you really don't pay attention to significant figures at all. You just pay attention to decimal places. Now with multiplication or division, again, you look at your arguments coming in. Let's say I've got a certain number of meters divided by a certain number of seconds to get a velocity. Count the number of sig figs, not decimal points, and take note of the number of the least amount. Then again, you will round your answer to the least amount of sig figs, not decimal places. So let's look at a quick example of that. Let's say I've got 2 values that I've measured coming in. I got 3.01 and I've got 7.002. In one instance, I want to add them, and in one instance, I want to multiply them together. So let's not round anything. Let's just plug this into our calculators and see what values our calculator spits out for this. And here are the values if I were just to do it in a calculator and not round it at all. Look at this first one. 3.01 times 7.002 comes to 21.07602. So if you were to collect this in lab, for example, and you just reported it like this without rounding it, I would look at this and say, all right, you got the 10th, 100th, 1000th, 10,000th, 100,000th. So you're telling me that based on the equipment that you used in our public school, you were able to measure to the 100,000th place accurately? And I'm going to call you out for that, because no, we don't have that kind of funding. So instead, we're going to use significant figures to actually round it to a proper amount. So 3.01 has 1, 2, 3 sig figs. 7.002 has 1, 2, 3, 4. Okay, well 3 is less than 4, so I'm going to round my final answer to just 3 significant figures. That'll come to 21.1. All right. Now over here where I add them up, I got 3.01 plus 7.002. Because I'm adding, I'm not looking at sig figs, I'm just looking at decimal places. I got 2 decimal places from 3.01, I got 3 decimal places from 0.002. 2 is less than 3, so I'm going to round mine to 2 decimal places. 10.01 is what it'll come to. Now when you're adding, it looks like you just picked up another significant figure, right? Because 10.01 has 4 sig figs, 3.01 only has 3, but we don't care about sig figs while adding, just decimal places. And finally, to wrap up this video, let's talk a bit about uncertainty. Now, no measurements you're going to take ever are going to be perfect. I don't care how good your equipment is. So, to indicate how confident you are, you both use significant figures and an uncertainty value. A lot of times, let's say my measured average, I ran an experiment over and over and over again, came up with an average. I'll just place a letter A there to indicate the average. It's probably actually a number, but we're just going to use the variable A for right now. Now uncertainty, this is a funky little Greek letter, delta. So that's just delta A, indicating the uncertainty amount. And you'd see the final report as some value A plus or minus some other uncertainty value. So an example of that would be 273.2 plus or minus 1.25. That means, yes, my average is 273.2, but I'm not exactly sure if that's what it is. It could be 1.25 higher, it could be 1.25 lower. So this would be my A value, this would be my delta A value. Cool. Now to determine uncertainty, Here's a quick, kind of simple example. Let's say I'm counting raccoons. So the raccoons from the previous lecture loved my cupcakes, word spread around to the raccoon community, and now they're all piling in. So I need to count the raccoons to figure out exactly how many there are, so I know how many cupcakes to make, so I can appease them and avoid a raccoon uprising. Obviously. Now, I stayed up all night the night before watching Xena Warrior Princess, so I'm a little bit tired and my counting skills are not where they need to be. So every time I try to count, I'm getting a different number. Let's say on average I counted 25 raccoons, but I might have double counted one or I might have missed one because they're shifting around like their little raccoons tend to do. So I could report 25 plus or minus one raccoon. Could be anywhere from 24 to 26. Sometimes you'll see it as a percent uncertainty. On scientific papers, it's this value with X percent uncertainty. I'm not really going to have you all do that all that much. But just so you know where that comes from, that's that. Now, this wasn't really a good example, just because uncertainty values are not guesswork. Actually, nothing in science is guesswork, even if it's called a theory, which that's a rant for a different time, because theory and standard speak is different than theory in science, and it's not just it's peer-reviewed. It's all rant for a different time. So, uncertainty value can be found with a tool we call the standard deviation. Now, you can find standard deviation by hand. If you've got a whole set of data, then you can find it by taking the average of your set of data, then go to your first data point, find the difference between that and your average, square it, go to your next data point, find the difference between that and your average, square it, next data point, all the way through, divide it by your number of data points, and take the square root of the whole hunkin' thing. But that takes a really, really long time. So as another example of what you can do, you can use this beautiful, glorious computer program called Microsoft Excel. So let's do an example with the raccoons again. Let's say on my first attempt I counted 25 raccoons, on my second attempt I counted 26, on my third attempt I counted 24, blah, blah, blah. I end up with 10 attempts, and on average I got 24.5 raccoons. To find the standard deviation in something like Excel, I would type equals STDEV, open parentheses, and highlight my data, close parentheses, and ta-da! I did not have to take each data point, subtract 24.5, square it, and all that gross stuff. It just did it for me. Now, I need to round this for Sigfigs as well. Ooh, I need to do that for my average as well. I didn't even think about that before. So average is now 25 when I round it to proper Sigfigs, and 1.7 is my standard deviation. So I could say I counted 25 plus or minus 1.7 raccoons in my basement. And with standard deviation, within one standard deviation of your average, here's your average right here. It's marked by a little mu. If I go plus or minus, 68% of my data should fall in there. So that's a pretty good confidence range. If I decide that I really want to be more confident than that, I could change my plus or minus value to be 2 times the standard deviation. And then I'm going to get a lot more data falling under that umbrella. But we'll talk about that when we actually do a few more labs. Right? Take it easy.